welcome on behalf of the Hampshire branch and also on behalf of the Green IT, not to mention the Sussex branch as well. We're very, very lucky to have Gary with us, and it's a very special day. It's Clean Air Day, and this is probably one of the clean air days that have actually had the cleanest air around. But unfortunately, it's because of the virus rather than actually the activities we've been doing, I suspect. Now, at that stage, I'd like to pass on to Gary. Thank you very much, Gary.
Margaret, thank you. Thank you very much. And to all of you watching, thanks for taking time out of your busy lockdowns to join this webinar. So over the next 40 or so minutes, I'm going to talk through a series of slides which will essentially talk about some of the higher level challenges associated with monitoring and understanding air quality. And I'm then going to talk more specifically about some of the lessons that I have learned on this journey and hopefully share some of the experiences, both good and bad, of grappling with the challenge of measuring air quality, but not just measuring it, but finding a way that we can actually then subsequently do something about it. A repeating theme throughout this presentation is going to be this idea that actually it doesn't matter if you sense everything in the universe. If you don't actually do anything as a result of that insight, as a result of that data that you gather, you're kind of wasting your time. But first of all, let me introduce myself to you. Hello. My background has been very much, really for the last nearly 40 years, in fact, I've been involved in technology in one way or another. I started as a nipper with a ZX81 and wrote software for some of the very early personal computers. I've worked on the Burroughs mainframe and the Unisys mainframe, the IBM mainframe. I worked as part of a team introducing client-server computing to Ford Motor Company in the 1990s. I've been a CIO. I was the IT manager and membership manager for the Royal Yachting Association for a couple of years. But I spent a good chunk of my time working as a research analyst for a couple of the big research firms, figuring out what's happening with technology and giving people advice on how best to use, embrace and adopt new technologies as they come along. For the last decade, though, I've been really, really interested in the Internet of Things and in getting these insanely powerful and tiny components, some of which you can see on the screen now, and many of which I suspect you'll recognize, to do amazing stuff. So I'll give you a very quick tour of these processors. The tiny little six-legged critters that you can see on underneath the About Me text, those are 80 tiny chips. They're microprocessors that are about 3 millimeters long and 2.5 millimeters wide. And you'd imagine that there wasn't a great deal you could do with those things, but in fact, you can do all sorts of clever things with those. You can certainly operate a wireless doorbell. You can operate a TV controller with them. Those are surprisingly powerful little components, and we can go through. Some of you will recognize the Raspberry Pi Zero at the top middle there. An incredibly powerful machine that runs Linux. It's a multi-user, multi-process operating platform, and that's designed to be embedded and incorporated within solutions. But that's still an awful lot of compute power, and it's in fact a lot more compute power than we need for a lot of the things that we're doing. At the bottom, there are a couple of examples of ARM processors, which are the processors that we use in a lot of the air quality monitoring technology. But just for fun, on the other side of the screen, we've got an NVIDIA Jetson board, which is a profoundly powerful computing platform. It's certainly got as much power in a single board, which is about 25 centimeters by 25 centimeters, as there was in the first 2 or 3 mainframes that I worked on. It's an incredibly powerful device, capable of doing all sorts of processing, particularly around machine learning, AI, image manipulation, signal processing. And that's the kind of board you'll find in the very intelligent high performance edge devices, and indeed some of the air quality monitoring platforms that we use, because of the number of different phenomena that we're measuring, might indeed end up using technology as powerful as that. So that's the background for you. I'm primarily, though, a software engineer. So this discovery of Internet of Things and discovery of hardware has been incredibly interesting and at times challenging tasks to take on. And again, I'll be sharing some of those sometimes hard-won lessons. I'm sure that you've all been in a room at some point when some idiot has said the words, "How hard can it be?" And my journey with air quality monitoring began with me being that idiot nearly a decade ago, when talking about the challenge we face in understanding the impact of poor air quality on health and the cost associated with measuring air quality in a meaningful and usable way. And I was the fool who said, well, how hard can it be to measure air quality without having to spend tens and hundreds of thousands of pounds? And in the course of the next few slides, you will discover how hard it can be. But let's start by reminding ourselves, it's Clean Air Day today, let's start by reminding ourselves of the scale of the challenge. And one of the key components here is that this is not a one-dimensional challenge. There are many, many different factors that come to bear on air quality and the broader conversation around environmental quality. And it starts with the fact that even in the developed West, so let's set aside some of the mega cities in the emerging East, whether it's in India or China, where the massive rate of industrial and economic growth they've been experiencing has led to incredible issues around pollution, poor water and air quality. Even in the developed West, we have a significant challenge facing us in the context of air quality. And it's a challenge that is measured not in tens of millions of pounds, but quite literally in billions of pounds of cost to our economy and incredible cost in human life. These are stories that you will have seen many times before. There is no doubt the science is very, very settled that poor air pollution causes premature deaths, it causes premature ill health, it has significant impacts on the health of children who are often walking to schools along roads that are particularly polluted. And the fact that even in the UK, where we would expect to have very strong environmental protections, where we'd expect to have strong standards around the environmental impact of the built environment, the transport system, and all of the other components and elements and people that act within that system, this is a very, very big challenge. So, starting with that big question, how do we address the problem that poor air quality causes? We start with a number of very, very important challenges. One is, what do we actually sense? What phenomena are important? What things are not so important? Traditionally, and this is partly because air quality has always been very strongly and not unreasonably associated with traffic and transportation. Nitrogen dioxide and ozone are two really crucial components that we do need to measure on an ongoing basis. They have an impact on health. They help us to measure not just transportation, but also industrial activity. So they're good things to measure. And we've recently come to learn that measuring particulates in the atmosphere is also very, very important. And particulates come in many sizes. Measuring particulates that are around about 10 microns wide, PM10, is relatively easy. Those are the particles, by the way, that generally you could smell. They include pollen, although pollen tends to be somewhat larger than 10 microns. But whilst they're irritants, those aren't the really deadly particles. The really deadly particles are the small ones. At PM 2.5 or at PM1, these particles can get deep into your lungs and indeed Particles as small as 1 micron wide can actually pass through the lining of your lung and make their way into your bloodstream. So you're being polluted from the inside out as well as from the outside in. The next question is, how do we sense these different things, and how do we do so in a way that is accurate, that is reliable, but more importantly, with the third point on this slide in mind, that isn't fantastically expensive. We know that we can measure phenomena like ozone and nitrogen dioxide using very, very sophisticated and very, very accurate instruments, but we also know that those instruments come at a very significant cost. So how do we balance the need to sense accurately with the need to sense more widely and in more places? And of course, finally, how do we figure out how to pay for it? One of the key components of that is to drive the cost of doing the sensing that we need to do down as far as we can without sacrificing too much of the fundamental quality of data that we need in order to make informed decisions about what's going on. Now, because the traditional cost of monitoring air quality to regulatory standards has always been very, very high, and we're talking about costs for a standard air quality monitoring station varying between £50,000 for a unit that senses relatively few things to sometimes in excess of £250,000 for an air quality monitoring station that senses a lot of things. Given that price, it's no surprise that we don't have thousands of them littered about our cityscape or our countryside. But we do need more localized data in order to help understand the experience of a cyclist on their commute to work, or someone who's walking to work, or children on the school run. We need to have a much better sense for what the data is at a much more hyper-local level. And yes, we can use modeling. Given a small number of data points, we can come up with some fairly good estimates about what the data is like in particular areas, but it's still nothing like fine-grained enough for us to draw really, really sensible conclusions about how we should potentially change our behaviors. The things we need to sense vary, and of course what we want to do is we want to measure pollution as it's experienced by people. So wherever people are, we need to be measuring the quality of the air that they're experiencing, whether that's at home, in the countryside, whether that's at work, whether that's on their travels. And of course, we also want to understand the impact upon air quality of these other activities, whether it's transportation, shipping, heavy industry, or indeed farming and agriculture. One of the claims, by the way, that Jersey make about their cows is their cows produce less methane on average than other cows do. So if there's another reason to buy your butter from Jersey, you can satisfy yourself that less methane is produced in the creation of Jersey butter than other butters, apparently. I was told that by a Jersey person, so obviously there could be a little bit of vested interest there. But we need to measure all of these things everywhere we experience the pollution, everywhere that air quality is likely to have an impact on us, our health, the health of our friends, partners, and children. If you really want to understand air quality, then you have to measure it where it's experienced, and crucially, you have to be able to put that data to work. Data doesn't have any value unless it provokes some action. So it's no good just collecting the data. We need to figure out ways of putting that data to work. And more importantly, when it comes to making decisions on the basis of data, we have to really understand the provenance of that data, its quality, its full life cycle, who created it, and who is responsible for monitoring and managing it. And this is actually of strategic importance to us as a nation, as increasing parts of our vital national infrastructure depend on data gathered from environmental monitoring networks and other networks of sensors. We need to be really careful that we're thinking about reliability, resilience, veracity, validity, provenance, and security in the context of data as well. So let's start with Manchester. So at AirSensa, we're running a couple of fairly large pilots, one on the island of Jersey, hence my unusual knowledge about methane production by Jersey cows, and another one in Manchester. This is a picture showing the DEFRA's air quality monitoring stations in Manchester, and you can see essentially there are 3 of them. Now, these three monitoring stations are very accurate, they're very well managed, they're very, very precise, but they don't provide hyper-local data. We can infer some things from these. We can certainly come up with a macro level view of what the impact of air quality is on Manchester as a whole, but we need much more localized data measurements in order to come up with interesting responses to air pollution, whether it's managing traffic in a more intelligent way, whether it's managing people, helping people with chronic lung conditions to choose a better route to work. We need to drill down and get much more localized data. So this is a map showing the centre of Manchester, and these are units that we've already deployed and that are already operational. Many of them have been deployed by Transport for Manchester, so many of them appear at traffic lights and road junctions. And Transport for Manchester, by the way, have been absolutely fantastic in supporting us. They essentially covered the cost of deploying these for us, and have been a really supportive partner in this process. In addition, we've partnerships with Salford University, Manchester Metropolitan University, and Manchester University, and I'll talk about the importance of partnership later on in this presentation, because that's also a crucial part of getting this right and doing it right. But you can see there what we're trying to do is create a much more dense sensor network, so we can start getting much more localized data and start analyzing that to produce really effective hyper-local measurements and hyper-local maps of pollution in the built environment. There's a big discussion about sensing technologies, and one of the reasons we've been able to deploy this many sensors is that we're not deploying the £200,000 ARUN DEFRA standard units. The units that we're deploying at this stage are quite literally an order of magnitude less expensive. The units we're deploying cost between £3,000 and £3,500 each. That's still quite an investment. But whilst they obviously don't produce data that is at the same level of precision as the very high fidelity and very high cost units, they produce data that really does correlate very well with those units. So this is not about replacing them. In fact, it's about adding additional texture that can help us with the analysis and modeling that we want to do to really get to the bottom of understanding hyperlocal air pollution. I want to talk a little bit about the different sensing technologies, because there's a little bit of politics and religion here, and there's also a real need for us to figure out ways of lowering the cost of doing sensing effectively. So I've got, broadly speaking, within the world of air quality monitoring, there are 3 tribes. There's the statutory monitoring tribe, who for very good reasons want data that is extremely accurate. And it's very important to them that not only is the data accurate, but the processes involved in managing the sensing hardware are rigorous, because this is data which is used in defining regulations, in writing legislation. So there's a quite understandable desire to monitor at very high levels of precision. But of course that comes at a cost. And at that £50,000 to £200,000 price mark, this is not something we can put in every school or put on every street corner. There is a slight tendency of fans of this type of technology to look down upon mid-cost monitoring solutions, which are not extremely accurate, but they are pretty accurate. Those of you who are statisticians will know that if something has an R² of in excess of 0.95, it is a pretty strong correlation. And the units that we use, of which there's an example there, which are manufactured, as it happens, in New Zealand, correlate extremely well with those high-end units, but they're significantly less expensive. But even at £3,500 a unit, you still can't deploy those at massive scale. And one of the big challenges that I'm looking to address is to figure out how we can deliver low-cost monitoring that doesn't replace either mid-cost or statutory level monitoring, because they simply won't compete in terms of absolute precision. But what can we do with very low-cost monitoring to add more data to our model to enable us to draw better conclusions? So instead, perhaps, of monitoring ozone and nitrogen dioxide, which are notoriously difficult phenomena to measure, what could we learn if we were measuring pressure change, sound, and vibration? What could that tell you about what's going on within the cityscape that might allow you to draw some inferences around pollution? The other thing that we can now measure really quite accurately, but again not at massive cost, is particulates. Again, I have a particulate a monitoring device in my laboratory that cost over £25,000, and again we can't litter our landscape with those, but incredibly $25 particle counters perform surprisingly well. Again, they're not as good, but they do give us a very strong indication of what particle levels are like. So there's, I believe, a room for all three types of sensor. You'll find there is a slight tendency of people who belong, and particularly people who sell the high fidelity technology, to be very sniffy about mid-cost and low-cost sensors. People who sell the mid-cost ones, it's a little bit like the Monty Python sketch, dismiss the expensive guys as being way too expensive to be useful, and of course they dismiss the very inexpensive guys as being way too inaccurate to be useful. And then finally, you've got the scrappy upstarts at the bottom of the heap. They're saying, well, all those guys are way too expensive. We're great, and you can just rely on our stuff. And of course, that's nonsense. The only way to really understand air quality is to deploy a blend of the right sensors and the right sensor types for the context within which you're working. So ideally, yes, I think Manchester should have more than 3 statutory air quality monitoring stations. I think for Manchester, the number should ideally be between 8 and 15. But we can add to that a much bigger cohort of those mid-priced or mid-cost air sensors, and then we can add another factor of 10 or even 100 times more of the smaller units. And the smaller units, incidentally, if we design them right, can be battery powered, so there's very low cost associated with the deployment and maintenance. But it's about finding the right balance of sensing and sensing the things that make economic sense to measure. The other important component about the first 2 classes of sensing, the statutory sensing station and the mid-cost ones, is that they do need to be calibrated regularly. The mid-cost sensors use electrochemical sensors, which are notorious for drifting over time. So they need to be taken back to a lab and properly recalibrated and then redeployed in the field. And that creates other challenges, which I'll talk about in a few slides' time. So we've got lots of things to sense. If we want to sense lots of things, we need to deploy lots of things in the built environment. And again, deployment is a huge challenge. Where do you deploy them? Who puts them up? We were lucky in Manchester, in that Transport for Manchester was willing to go to the trouble of deploying many of our sensors on their traffic lights. The cost to deploy one of these can be very, very significant. The statutory and the mid-cost air quality monitors typically require a mains power supply. As soon as you need access to mains, you need a qualified electrician to install them. So there's a deployment cost as well. And once you've deployed them, you need to manage and maintain those things. It's no point just leaving them there. There needs to be a rigorous and valid process for keeping these things up and running and working. And of course, there's loads and loads and loads of data to wrangle coming out of these devices. And again, with electrochemical sensors, we have to think about calibration. We have to think all the time about data quality. So one of the things that we're very, very, very keen on is that whenever we make some change to the data, that we record what that change was and why we made it. So if we change the calibration settings on a sensor as a result of some calibration exercise, we record the fact that we've done that, so that later someone could actually go back through the data and understand every single change that's been made to it, so that the data can be transparently reviewed by an independent third party, so that we can show exactly, if you like, we're showing our working. And that's going to be increasingly important. The whole idea of a black box where some dark equations are applied to data isn't going to work in future. So we want to be more transparent and clearer about the data that we're sharing and the assertions that we're making. So quite a big challenge, and I'll wrap it up. You know, the air quality is a huge issue. It's costing billions of pounds a year and harming many hundreds of thousands, if not millions, of lives. We need to sense that data, sense air quality wherever it is experienced, which means in the home, in the office, on public transport networks, in the cityscape, and indeed from time to time in the countryside as well. Inherent in that is the challenge of picking the right sensors, deploying them, and once they're deployed, managing them, and then finally we have the challenge of gathering the data. How hard can it be? And I've been at this for nearly a decade in my spare time and at it full time for 2 years, and I can say to you with a great deal of certainty that the answer is that it is flipping hard. This is really, really hard, and it's hard for a number of reasons. But one of the ones that has challenged me the most is the fact that you need to be multi-skilled to do air quality monitoring. This is my desktop, and it has been my standard desktop for many, many years. As a researcher and an analyst and a thinker about technology, and as a software engineer, this has basically been my workshop. My headphones, well, okay, the liquid hand rub is a recent addition thanks to COVID. Quick shout out, these are made in the New Forest near where I am, absolutely fantastic. 97% alcohol and smells very much like a very nice gin. Not that I've actually tried it, but that's my traditional desktop. But since getting involved in air quality monitoring, I now have 2 desktops, and my other desktop is a gnarly laboratory desktop. You can see there my solder station, Dremel. You can see the broken shell of a soil moisture meter, because one of the things we're developing is a LoRa-based soil moisture measurement device, which hopefully will cost less than $10 a pop. So I have to switch between being a software engineer and all of the interesting things that implies, and then switch into being a hardware engineer, which brings a whole new set of interesting and exciting challenges. But fundamental to air quality monitoring is that this is an IoT challenge, and the IoT and air quality is about software and hardware. So starting at the hardware, this is a prototype of an internal air quality monitor currently being tested on my bench power supply there. This device measures volatile organic compounds, sound, temperature, light, carbon. Well, it does equivalent carbon dioxide, but I also have a separate module. The gold-colored module is a laser-based carbon dioxide module as well. It communicates via LoRa, which is a very low-cost, relatively low bandwidth communications network, and it sits on a board that looks after power supply and makes sure that we meet various regulatory standards. So this is an ESP module, an ESP32 module, which some of you will recognize, which does all the thinking, combined with a couple of external sensor packages. And we're developing a lot of different types of hardware. So the picture on the left shows a collection of our prototype indoor air quality monitors. They're inside a calibration chamber there, essentially just being test run prior to deployment. We use LoRa a lot, and that the box with the two aerials is a LoRa gateway. Essentially, inside there is a Raspberry Pi, an 8-channel LoRa radio, and some awesome software. We currently use the Things network because it's a brilliant platform, and even more brilliantly, if you're willing to essentially provide a gateway, you can connect up to 1,000 devices to their network free of charge. So I'm a big supporter of the Things network. The third device is on my proxy a lamppost. You can probably see one over my shoulder. That's the external air quality monitoring device that we're currently deploying in Jersey and Manchester, and below it is a waterproof power supply. The fourth device is the top of a solar-powered box, which is a prototype that we're going to use in a number of different applications, one of which will be particle measurement. The other one is experimentally for water level measurement in streams and watercourses, and also for soil moisture measurement. That's quite a big solar panel. We're starting with that. If we can get it to work with that, we intend then to essentially lower the power drain and hopefully end up using a much smaller solar panel. But everything we do is about trying to be a bit modular and a bit clever. So every bit of development we do, we try and make sure it's applicable for more than one sensing scenario. We just can't afford the time, and time is the biggest constraint for us, to develop multiple stacks of technology. So we're working very hard to have a standard hardware reference model that we can replicate across different sensing scenarios. But now we get into the weird world of firmware, which is mostly software, but it lives in the heart of hardware. So we write our firmware in C and C++. We use free RTOS, and this is really, really gnarly stuff. Writing firmware is fabulously difficult because you don't have any slack, particularly once you've started deploying devices. Because in the happy days when all I'm doing is working on cloud software, if I make a mistake, I can just FTP into my cloud service and update everything. Unfortunately, particularly when your devices are on a LoRa network, you can't do over-the-air programming. You have to get it right first time. So the amount of testing that we have to do with our firmware is absolutely boggling. On our data platform, we have chosen Google's Golang programming language. I can do a whole seminar on why I picked Golang. I have never regretted it. It's an amazing programming language, particularly for high performance web services. And the key thing for me is it's very easy to learn. So bringing people from with a Java, a Ruby, a Python, or a PHP background to Golang is really easy to do, and people pick it up very quickly, and they're blown away by the performance that you can get out of Golang. The first service that I wrote in Go was for a weather site that was being used at the Rio Olympics to measure the wind speed and direction for the canoeing, and I think also the sailing. And we were in a huge panic about how do we get this application that had originally been written in PHP to scale to the kind of scales that we knew it was going to need to support. Over a weekend, I wrote a very naive caching service using Golang, and I started testing it, and I created a special program to allow me to create 10 virtual clients, then 100, then 1,000. And I stopped at 10,000 because I kind of started not to believe myself. But the scalability boost we get by using Golang and by very aggressively caching data is absolutely immense. And of course, we have a portal, and our portal is written in React. So that's JavaScript, HTML, the joys of CSS. It's completely decoupled, though, from the platform. This is a really, really fundamental design decision that I made a number of years ago, and I'm just delighted that I did. Part of the point of writing a good IoT platform is that actually your portal shouldn't matter, because most people are going to want to access your data from their portal or from their application. So this portal really is just a worked example of the APIs that we make available to people who want to incorporate our data. I mean, don't get me wrong, I think it's fairly pretty. Trust me, I didn't design this. We actually got a grown-up to do some of the design here. But it's a, it's a fun and easy to use way to interact with the data. And we chose React primarily because of the availability of skills. All of the portal side of our software is actually written by a very small team of people based in India. So I'm on regular calls with those guys, and essentially they interact just with the API. So we can have a separate team working on the server side stuff, and a team working on the client side stuff. We've also incidentally got mobile apps as well, currently written using React Native. This is the bit that I like the most, because I'm not a particularly visual person. That's why I'm a software engineer, I guess. But we have an API that is designed to make it as easy as possible for people to get hold of the data and consume it in interesting and useful ways. And we document that API so that third parties can readily access it. You'll be pleased to know, or at least relieved to know, I hope, that the platform is secure. You do have to have a valid token, and to obtain a valid token, you do have to log in a secure way. You can create API keys as well. So you can have a long-lasting token that you can manage, extend, or indeed revoke. And you can add different levels of permission to users, so that users can be limited to a certain set of sensors, indeed a certain set of phenomena within those sensors. They can be limited to a geographical area. They can the geographical area can be defined as a circle, i.e. a point and a radius. It can be defined as a square, or it can be defined as an arbitrary polygon, if you like that. And we implemented that because obviously someone asked for it. I think they were just testing us, but we implemented it anyway. So you've got hardware development, which is currently done here at the lab and by a partner organization in Lymington. We've got firmware development that is currently done in Southampton and Moldova. We've got core platform development that's currently done in the lab by us, and we've got the user interface development that's currently being done in India. So it's a pretty diverse and distributed team. It's still nice and small, and scaling to the next level is going to be a big challenge for us, I think, because at the moment I can still talk to everyone in the team once a day, and getting where we're approaching that point where we're going to have to change some of the structures that we have in order to scale up our development. Because scale is really, really important in this world. And it's important not just in terms of the software development, the hardware development, the stuff we do in the lab. It's also really important if you're trying to deploy a large-scale air quality monitoring network. And this is something that a lot of us probably should have thought about earlier, but I experienced this 4 years ago when we were running early pilots. You learn that it's the classic story of low-hanging fruit. Taking the low-hanging fruit teaches you nothing about how to get high-hanging fruit. Completely different skills. And deploying a small IoT network with maybe 5 or 6 devices teaches you next to nothing about how to deploy an IoT network that has several hundred devices in it. If you've only got 5 devices and one of them breaks down, you get on your bicycle, you go out, you can fix it. But if you've got thousands of these things deployed and they start breaking, you can't go out and fix them all. So you need to develop processes and develop ways of working that enable you to scale up. So interestingly, at least I would say a third, possibly at times even half of the development work that we're doing isn't actually about the data or the devices. It's about supporting the processes we need to have in place to manage the network in a secure and reliable way. And one little example, this is one of our lovely external units. That comes with a very basic bracket from the manufacturer. It's the kind of bracket that you expect to put on a lamppost and leave forever. But these things need to be calibrated on a regular basis. You can't have someone climbing up a lamppost with 4 screwdrivers and a hacksaw to try and change it. So we had to develop a custom bracket that attaches to the pole that allows you, essentially, the key design criteria here is, can I take that unit off and replace it with one hand, because the other hand is holding on for dear life to a ladder. So we've done some engineering to create a custom bracket that makes it easy to deploy and take these things off. And I did not imagine, as a software engineer, that this sort of stuff would be occupying my life. But this is the reality of learning how to do air quality monitoring networks at scale. The other challenge is calibrating these sensors. Now, quite a lot of projects get away with grabbing their devices and co-locating them with one of those high fidelity reference stations. And that, again, that's kind of okay if you've only got 1 or 2. You know, no one would complain if you co-located a couple of sensors. But if you're running a large network, I think DEFRA would get a little bit testy if we were surrounding their air quality monitoring stations with our own in order to try and get some calibration data out of them. So you have to develop a process to enable us to calibrate. And this is a very early prototype of a calibration chamber that we've developed. The two machines that you can see underneath that tabletop are fantastically expensive, high fidelity gas monitors. One is measuring NO2 and ozone, NO2, NO and NOx. The other one is measuring ozone. Those are exactly the same kinds of monitor that appear in the regulatory air quality monitoring stations. And between them, those cost in excess of £30,000. We use those then to measure the air inside that chamber. And where you can see the blank hole, essentially, we are injecting air from the ambient atmosphere. So we suck air from outdoors into the chamber and flow it through the chamber. We simultaneously measure the air using the high fidelity instruments, and we track the measurements that are being recorded by the lower cost instruments. We then compare that data. We run regression analysis and a number of other statistical models against that data to come up with new calibration factors, with the goal then of, at the end of that calibration period, of having new calibration settings for all of the devices that we have in there. And the schematic is very simple. We have an input box on the left where we draw air in. In the next version, we're going to add a mixing chamber, which allows us to add additional pollutants to the incoming air. We flow that air at a relatively slow rate through the chamber and exhaust it out. And we put any units that we want to calibrate inside it, and our reference instruments sit below it, but they're sniffing the air inside the unit. And the box at the top, which will eventually be a Raspberry Pi with a touch screen, essentially is controlling the speed of the fans, the mixing of pollutants, the switching on and off of the reference instruments, and the switching on and off of the instruments to be calibrated. And essentially the idea is that this is the equivalent of a dishwasher for calibration. You put the units in, you close it, you close the door, you press the green button, you come back 8 hours later, and all of those units have been automatically calibrated. And this is important because we can't afford to calibrate every one of these units in the old-fashioned way, using much expertise and many lab coats. We need to automate and productionize these processes. The other element to managing at scale is essentially managing the assets. So the background platform needs to be able to know where every device is at any one time. So, for example, we track when assets are in stock with a partner organization in one of our cupboards. So Totten Stock A is the left cabinet, about 5 meters away from me now. We also have stock locations for the flight cases we use to transport units. So when units leave one of our stock cupboards and go into a flight case, they get allocated to that flight case. So we can track that unit's whereabouts throughout its whole life cycle. And then we've got a process for adding and managing devices in order to, again, keep a handle on where everything is. We also manage the maintenance schedules, the service schedules. We also record any calibration and any modifications that are made, so that we can, again, provide someone with a full history of that device and all of the data that is produced. And in order to deliver the data at scale, we have to do all of those really basic things around delivering high-performance cloud services. Our target is actually that 5 nines, 99.999% of data requests completed under a second. That's still a little bit of a stretch, but we're very comfortable that 99.99% do. We cheat slightly with that, in that 99.99% of data requests are for data within the last few hours. A very small proportion of requests are for data outside the last 10 days. So we cheat and we cache 10 days of data in memory on our server. So those requests don't require any database access, and essentially the only bounding factor is the network bandwidth to that virtual machine. We need high reliability, particularly if people are going to start making real-time decisions based on our data. So again, building in those, I mean, let's face it, these are probably actually the minimum level of competence required, you know, rapid failover, rolling updates, levels of security that frankly all of you should, you know, immediately recognize as being the bare minimum we need to do. But that data integrity component is very important to us because we want people to trust the data, and part of that is being very, very honest about where it's come from, what its limitations are, and what we've done to it throughout its life cycle. Partnerships are also really important. Whilst you've seen a lot of hardware, actually it's not our goal to be a hardware manufacturer. We'd love to partner with other people who are developing great hardware. And many of our partnerships, particularly with the likes of the University of Portsmouth and University of Manchester, are around developing hardware that will be open sourced, so that anyone can develop great new ways of sensing air pollution and other environmental factors. Digital Jerseys have been a great partner to us. They've done a similar job to Transport for Manchester, but on the island of Jersey, supporting us in helping us deploy them. And people like IBM, TE, CBRE, who are a massive a property management company, are all involved in supporting us and advising us and helping us figure out how best to tackle this problem. And I can't underestimate the value and importance of partnerships. So I'm closing, coming to the end of the talky bit. But essentially, the key lessons that I have learned over the last 10 years of doing this in my spare time and the last 2 years of doing this in my full time is, it's really important, if you want to build a scalable air quality monitoring network, that you think not just about the devices, not just about the data, but also about all the operational processes you'll need to build to surround your devices so that you can effectively run the network. Understanding the capabilities of the sensor technology, and also being very aware that sensor technology is going to change very, very rapidly. We've seen the price of some sensing technologies fall massively in the last couple of years. Particle counters, for example, a half-decent particle counter 2-3 years ago was £300 or £400. Now you can buy particle counters with very, very comparable performance for much closer to £25. And we expect that sensor technology to be evolving all the time. The National Physics Laboratories come up with some very interesting new technology for measuring nitrogen dioxide. And again, we want to track that. And indeed, one of the uses of our calibration chamber is to benchmark new sensors as they come along, because I firmly believe that if any project's going to have a life cycle of more than 3 or 4 years, you can expect fundamental chunks of the technology in those sensors to change over that time. And obviously, find brilliant partners and collaborators. You know, it's a golden rule for me, which is listen to anyone who will talk and talk to anyone who will listen. This is an incredibly exciting space, and it's a very dynamic space. And the more collaboration and partnership that happens, frankly, the less reinvention of the wheel is likely to take place. And of course, fundamental to this, and particularly on today, given that it's Clean Air Day, my real takeaway to all of you is get on with it. Take this on as a challenge. If you want to know more, reach out to me. I'm happy to talk about more of the challenges and some of the ifs and buts we've encountered over time.